Melting points. Oh, dang it. Are you serious? I think I'm going to go back to my office. I did stick them in here. I did. So I put together this a while back. And it's been, you just have to ignore the little corners. Because we're going to talk about solids and how you classify solids. This is also in your textbook. But I put this together because it just makes more sense to me. So I'll be referring to this. But right off the bat, so right off the bat, you see, solids can either be amorphous or they can be crystalline solids. Okay. Amorphous or crystalline. I don't have anything else under amorphous, but I have several things under crystalline solids. Okay. Now, amorphous are, if you think of something that's amorphous, it's kind of like blah. Plastic, okay, the polyethylene is blah. Okay, of course the gray things are carbons, the white things are hydrogens. Okay, they're just kind of like long chains and they're, you know, not long branching. Over here we have kind of now these are then the crystalline solids. And when we think of crystalline solids, if you're like me, I know in General Chemistry 1 I emphasize that we have two types of compounds. We have ionic compounds and we have molecular compounds. With ionic compounds, I said they form crystalline lattice structures. Okay.
I'm sorry, is the polyethylene the liquid inside the bottle or the bottle?
It's the bottle. It's the outside. It's the plastic.
It's like flexible.
Yep. Yep. This is an example of an amorphous solid. Oh, come on, technology. Be my friend. Okay, anyway, yes. This is the plastic. Yep. And then there's an assortment of solids here, and we'll talk about them. But you see on the sheet I gave you, if you go under crystalline solids, you see network, metal or metallic, and then you see ionic. Okay, those are three. Okay, we'll talk about each one of them, but these are some examples. What? Okay, so I showed you pictures of three. There's a fourth one, which is just a molecular crystalline solid. And an example of that actually is going to be water. But molecules versus ionic substances, their intermolecular bonds are, we said, dispersion forces. That's the weakest of them. That's the dispersion forces. Ordinary dipole-dipole, and then hydrogen bonding is stronger than ordinary dipole-dipole. All right. So in general, molecular crystalline solids are generally low melting, kind of soft. They don't generally conduct electricity very well. So there's your cute little water molecules in its solid state. You can tell because they're nice and organized. This is what gives us our snowflakes six-sided kind of a repeating structure. So there's water as an example of a crystalline molecular, a molecular crystalline solid. So the network solids, they generally, well, they're connected by an infinite number of covalent bonds, which is kind of weird when you think about it. Okay, instead of intermolecular bond, or instead of even hydrogens, hydrogen bonding. So these are even stronger. So these actually melt at higher temperatures. Now we talked a lot about the temperature at which liquids transition to a gas, the boiling point temperatures, as an indication of the intermolecular bonds of the liquid. That's true. And actually, this is true to a certain extent. What temperature do solids melt at as an indication of their intermolecular bonds? So when carbon arranges itself, that's an example of a bunch of covalent bonds between those carbon atoms. Of course, we talked about three different allotropes of carbon. One allotrope of carbon is graphite. You can kind of see it there. This is another allotrope of carbon, diamond. Quartz, which is, has the repeating unit, 1 silicon and 2 oxygens, actually that is an example of a network solid. So the bond, in other words, connecting this repeating unit is another covalent bond. So you have a covalent bond between the silicon and the 2 oxygens, and then you have another covalent bond connecting it to its other buddies. So ionic solids or ionic crystalline solids are things that we've already kind of talked about. You have an alternating cation, anion in a crystalline lattice structure. When we talked about in Chem 2, we kicked off and had that list of intermolecular bonds. Remember what was at the top was ion-ion. So it's a relatively strong bond. And it makes, now I understand that, I think I got this right. Sodium chloride salt, you know, it just like dissolves in water. You're like, it really does that. That's a different thing than if you were to take sodium chloride solid and try to melt the stuff. Okay, it has a very high melting point temperature. I think this is kind of fun. Sodium chloride, for example, would not conduct electricity as a solid, but if you dissolve it in water, I've got all sorts of ions to go ahead and carry your electrical current. So picture of the alternating cation, anion, cation, anion in sodium chloride. And we call,
I'm sorry, so these are stronger than the, I guess I'm curious because a diamond, what's stronger than a diamond? Like that seems like that's really.
What's stronger than a diamond?
So why would these be, are you saying that?
The ionic compounds are stronger than a diamond? No, not necessarily.
Okay.
But remember when we're talking about these bonds, for instance, these are what we call intermolecular interionic bonds. And they are still weaker than a chemical covalent bond. And the diamond has chemical covalent bonds. Yeah. Sodium chloride. Okay. This is one of my favorites. The metallic solids. So like when you pick up, like in the lab or whatever, if you've done anything with like iron, a piece of iron, a piece of aluminum, okay, it's a metal and it's a solid. So basically those atoms are held together by these dispersion forces. But what I think is cool is the electrons generally can be said to delocalize around the atoms themselves, the valence electrons. So you kind of have a potential sea of electrons that can move. If you have an electron gradient, you know, electron rich over here, electron poor over here, basically you can kind of complete a circuit and have electrons flow through your copper wire, which is how you get electricity to your gizmo. I think that's neat. Solids generally, they're malleable. You can draw them into a wire, that's ductile. They have an assortment of melting point temperatures. They conduct electricity, like I said. They are good conductors of thermal energy. So the pluses there are kind of the nucleus of the metals along with their non-valence electrons. And then the little blue things are the valence electrons, kind of creating this potential sea of delocalized electrons that can scurry down within your metal. I think that's cool. Okay. So what temperature would something melt at? What temperature would something melt at? Well, we say that temperature actually can, sometimes it's a temperature range if you kind of have an impure solid. The more distinct your melting point temperature, the more pure your substance is. But generally we say that it's when your crystalline lattice structure kind of collapses. And I like this word collapse. So if you guys go on to take your next stop in chemistry, most likely be organic chemistry. And in organic chemistry, you definitely pull out the melting point apparatus to do melting point temperatures. And you'll actually use like a little magnifying glass to actually see the solid collapse into a liquid. That's kind of fun. Okay. Let's see if this will pull up. Okay. So the temperature at which something melts at, you would think that the stronger the intermolecular bonds, the higher the melting point temperature. Kind of like the stronger the intermolecular bonds for boiling points, or for liquids, then the higher the temperature it would boil at. But actually there's another factor, and we'll look at it, an example of it in its symmetry. So there is a trend, and I'm going to show you with just normal alkanes, that the bigger the alkane, the more the intermolecular bonds, those dispersion forces can kick in, and you will have higher melting point temperatures. But this thing about symmetry can fit in. And I've got an example. Basically, the more symmetrical it is, you're going to see the higher the temperature that the solid will melt at, the more symmetrical. And so I have an example here of two isomers of types of dichloroethanes, but they're two different dichloroethanes. Do you remember the other day when I said we have the trans version and then we have the cis version? Trans is kind of going catty-cornered, cis is going on the same side. The thing to remember is if you have a carbon, double bond carbon like you have here, basically you have no rotation around that. And if I were to look at any one of these four carbons, I would come up with sp2 orbital hybridized. I would come up with trigonal planar. So basically you have two trigonal, kind of a pair of trigonal planars all lying in the same plane. So that darn thing is flat as a pancake. So with that in mind, you kind of have these fixed conformations where you, or fixed situations where you can have a cis, that's where the two chlorines are like this, or you can have the trans where the two chlorines are like that. Okay, so first off, see if you guys buy this, that this one is polar and this one is nonpolar. And this kind of goes back to what we talked about earlier in the class. The fact that you're definitely, of your tug-of-wars, that's going to be your culprit right there. Your chlorine is partially negative. Your carbons, in this case, partially positive, partially negative. All right, so definitely if you buy what I told you, the thing's as flat as a pancake, then you definitely kind of have an uneven, partially negative over here and partially positive up here. Well, if we compare that to this one, okay, so spatially, again, you have to think flat. So if this is partially negative, those are your hot spots. The center of those guys is right here. It's a plane. Okay, and then I don't care how else you want to do it, you know, these bring a degree of polarity, but we said don't worry too much if you have, you know, that's not a really very polar bond. But even if you did, you definitely have symmetry, kind of, meaning that the centers of negativeness and positiveness coincide, and that's what makes this darn thing nonpolar. So hopefully you guys would buy the thing that's polar will have more stronger intermolecular bonds. It boils at 60.3. And the thing that's nonpolar will have weaker intermolecular bonds. So it should boil at a lower temperature. Ta-da! It boils at a lower temperature. Well, before I go on, well, I'll go ahead and show you the next one. Well, here's the melting point temperature. Negative 80.5 degrees Celsius for the cis version. Okay. So if it's about polarity and nonpolarity, we would expect the nonpolar one to melt at a lower temperature. Okay, because it's less. It's going to melt at a lower temperature. But here you go. I know it's cold, but it's still higher. Negative 50 is still warmer than 80. So it melts at a higher temperature. So we have something else going on, and it's, like I said, symmetry. So you're like, well, how do you define symmetry? Well, there's a couple of different ways. But with this one, the one over on the nonpolar one, the trans version, actually you have symmetry basically kind of around a point. You have a lot of symmetry. Now I understand sometimes students will say, but Mrs. Snipes, you kind of have symmetry here along a plane, you know, tit for tat, okay? Symmetrical. And you kind of have something, you have a point with that. but this is a more sophisticated symmetry. So I told you, actually, this is going back to what we talked about with boiling point temperatures. We said that as you get larger, these, by the way, are all normal alkanes. I hope when you think normal, you think hot dog. Okay? These are just the long ones. Alkanes, I'm hoping you think hydrocarbons, all single bonds. Okay? So basically, these are increasing carbons. This 1 carbon, 2 carbon, 3 carbon, etc. You know, all the way up to 12 carbon normal alkane. The density increases, the boiling point temperatures increase, and the melting point temperatures also increase. All right. So just a couple more slides about the amorphous solids. So we said plastic was an example of an amorphous solid. But things that are brittle, like glass, actually, since there's no ordered structure, when they break, they just kind of shatter. Okay.
Can you go back there just about to get that?
I can't. So on to the next part, phase diagrams. Okay, so a physical phase diagram. Your physical phases are, aside from plasma, are solid, liquid, and gas. Those are your 3 physical phases. So a physical phase diagram shows all of the physical phase, those 3 physical phases, and it shows them in terms of pressure and temperature. So sometimes a physical phase diagram, pressure, temperature, phase diagram, it's the same thing. So always along the x-axis you have temperature, and along the y-axis you have pressure. So you kind of see the 3 different colors. Those little dots actually represent the 3 physical phases. Okay, so the red ones is matter that's in its solid state, the blue ones matter in its liquid state, and the tan ones matter in its gaseous state. Now this is every substance has its own diagram. Okay, this is just some random diagram. I'll be kind of talking about this Y. Can you kind of see this Y shape? Okay, that's kind of characteristic of a pressure, temperature, physical phase diagram. Okay, so in general, pressure goes up as you go up, and temperature goes up as you go over to the right. Okay, so in general, if we focus on kind of for this graph, the upper left-hand corner, that would be what? Low temperatures, right? And that would be high pressures. So we say kind of solids up there favor those conditions. If you think of an ice cube, okay, it's best if it's cold. And actually, ice may not be a good example, but solids in general favor high pressures. At the other extreme, over here, okay, this part of the Y over here, if you think about this, this would be high temperatures and low pressures. And actually, remember when we talked about the ideal gas law equation, we said an ideal gas will behave ideally at high temperatures and low pressures. Okay, so, and liquids are somewhere in between. They always are, with regard to temperature and pressure. So that's kind of what we have going on. Now this is for the substance iodine, I2, I assume. Okay, you can kind of see the Y. And one of the things you're going to want to be able to do is to kind of find your way around. Okay, solid, liquid, gas. Okay, so find the curve that begins at O, which is right here at the center of your Y, up to the point C. So this curve right here. And think about what it means here. Well, it is the line that separates a gas from a liquid. It's a line that separates a gas from a liquid. Actually, when we looked at these equilibrium vapor pressure curves back in part 5, I think it was, that was the segment that we were looking at for the substances. That's your equilibrium vapor pressure curve. Let's look at another segment. Let's find OB. So here's O and here's B. This is one of my favorite ones. Okay. We talked about, I think, the phenomenon called sublimation. If you picture what OB means, it's basically a substance can go back and forth between its solid and gaseous stage if you kind of tweak it. The way these work, and we're going to look at some examples. For instance, if you had, a solid here at this particular temperature and pressure, if those were like where your sample was, okay, do you see where if, for instance, you were to jack down the pressure, you could actually get it to go from a solid to a gas just by reducing the pressure. I think that's so cool. Okay, so that's OB. OD then would be the line between a solid and a liquid, and that's actually what we were just talking about, kind of the melting phenomenon. Notice that oftentimes doesn't look to you like OD is like straight up and down, like perpendicular to the x-axis. It feels like it. Well, sometimes, and actually we're going to kind of look a little bit at how water is got kind of a negative slope, and other substances generally have a little bit of a positive slope there. But that's where your melting and freezing is going on. Okay, I'll talk more about this here in a minute, but the center of the Y looks like an important point. Not the curve, but just the point O. That's actually what we call the triple point. And it is an important point for substances. Again, all substances, each substance has its own little physical phase diagram. Of course, triple meaning 3, and it's the 3 physical phases can actually coexist at that pressure and at that temperature. Cool, cool. And then we have a point that's kind of hiding, and we'll talk more about this. I'll kind of introduce you to the idea. Up here, point C, which is where your equilibrium vapor pressure curve, between your liquid and your gas is, we'll put it this way. As far as I know, and I could have looked at this up a little more, as far as I know, this goes to infinity. That line there goes up forever. Okay. You figure, this has to start at 0 Kelvin, absolute 0, and 0 pressure. But this actually, there is an end to this equilibrium vapor pressure curve. And you'll be like, well, what happens above with regard to pressure, and what happens at higher temperatures? And my answer actually is on this slide, and I double-checked it before I came to class. You can kind of think of drawing another sector up there, line going up here from what we call TC, stands for critical temperature, and PC stands for critical pressure. You can kind of think of drawing a line up there, and all of that is supercritical fluid. Supercritical fluid is SCF. So you're like, oh my gosh, I just never thought of this. So it's like another physical phase of matter. Kind of. It's actually got properties of being a liquid and a gas. So there you go. That's it in a nutshell. Oh, not quite. Okay, so we talked about, remember when we talked about the normal boiling point temperatures of substances, and we said that you can actually use, for that substance, its equilibrium vapor pressure curve, which is O to C, and basically find atmospheric pressure and come down and find the corresponding temperature. So that actually, 184.4, that is the boiling point temperature right there. This is your boiling point temperature. Normal boiling point temperature. And then over here, this actually, again, at 1 atmosphere, this is your freezing point temperature, FP. 113.6. Okay. physical phase diagrams, pressure, temperature, physical phase diagrams, pressure along the y-axis, temperature along the x-axis. So that triple point there, if you kind of think of drawing a Y, where I guess the left part of the Y kind of goes to infinitum, okay, and then the right part of the Y has an abrupt stop, okay. That intersection, like I said, is where the three physical phases of matter will exist in equilibrium. Beautiful harmony. The critical point was that abrupt end to, that was the C, point C, where basically your equilibrium vapor pressure curve stops. And it has ordered points of TC and PC. So I was thinking about this. I was like, oh, that is pretty darn cool. So just talking you through how do you get a supercritical fluid. Well, you can take a liquid, and we know that if you take a liquid and you add heat, that the intermolecular bonds will be broken and that thing will turn into a gas. But here's the catch, like this says, we're gonna, and I have little images to show you. Basically, we're gonna cap that thing off, okay, and we're gonna make it a stay system. Okay, so basically, like this says, as your liquid heats up, okay, it will drive, some of its liquid will go into its vapor phase. The density of the liquid will become less because it's heating up. The density of the vapor will increase because more liquid is going into its vapor phase. Okay, so you kind of have both of those going on. I'm kind of going down, here's your liquid, here's your vapor. Okay, eventually the two densities are the same. Okay, and what you're going to see here in a minute, when that happens, basically you can't see the meniscus between the solid and the gas. Okay, and at that point, if your pressure is right, you've raised it to a temperature where basically both of those substances, you neither have a liquid nor a vapor, you basically have a supercritical fluid, which is in that sector, like I showed you a minute ago, kind of up and over part of your pressure temperature phase diagrams.
What does those fluids look like if you would actually have one, since they don't really look like a gas or a liquid? What would that look like?
Let's see, what did I read? I think it looks more like a gas. I think it's, yeah, you don't see the, yeah, it looks more like a gas, but it has properties of a liquid too. Yeah.
Isn't it dangerous to get, like, if you have a closed container without, like, putting so much pressure on?
Yeah, this is assuming that you have the glassware or the hardware to contain that, which you're right, yeah. Pressure.
It could explode.
Yeah, yeah. But what we're going to see, and I think this is right, actually the carbon dioxide has a relatively tame critical pressure. So, yeah. Don't know what this substance is, but we have liquid and we have, I don't know if it's water maybe. So we have liquid and we have gas, and this is the closed system. So it says it's 10 degrees below the critical temperature. We're going to heat it up, and you see that separation between the liquid and the gas kind of being fuzzy, about 1 degree below the critical temperature. And at the critical temperature, like the slide says, you really can't tell. You can see kind of a shadow where you have your liquid and your vapor, but their densities are so roughly, they're kind of one happy family, and it does look more like a gas. And it's permeable like a gas, but it has the extraction features like a liquid, which is kind of what makes it so great. Your textbook talks about how, and I think it is, carbon dioxide can be used in its supercritical fluid state to extract caffeine from coffee. Okay, so that little point C up there, okay, had ordered pairs, the critical temperature and critical pressure. But the critical temperature can be described as the minimum temperature at which the substance will be in a gas phase regardless of whatever pressure you set it at. So supercritical fluids, like we've been talking, they're kind of on your homework, you guys are going to be doing this. And I apologize for your hints right now for your homework. They are pretty ugly. Hopefully you guys will do a better job. So if you're asked to draw a phase diagram, you might do it something like this. Okay, and it's your triple point right there. Of course, this is solid, liquid, gas. This is what this is talking about. This is your point above which that this is your supercritical fluid. So your critical temperature is right there, T sub C. Your critical pressure is right there. All right. So there's that again. And there's this. Did you guys have this one?
Same as the other one, isn't it?
Yeah, it is. Okay, so this one does some moving around on the, that marker's terrible. Okay.
Whoa.
This one does some moving around, okay? So this is called an isotherm. Do you buy that? And in chemistry, or this is chemistry. In meteorology, we talk about isotherms, basically holding the same temperature. So notice that if you go, you increase the pressure, it's kind of what the arrow is showing, from a vapor to a liquid, you start out with a vapor, okay, down here at this given pressure, at this given temperature. You hold the temperature, if you pressurize it, it's going to liquefy, okay? And then this says, if you go ahead and, if you start here, now we're changing the temperature, we're holding the same pressure. If we increase the temperature, it's just going to go from a gas to a gas. We're nowhere near anything interesting like a supercritical fluid. Okay. But if this point up here is indeed your C, we'll just keep calling it C, if that's your abrupt end to your equilibrium vapor pressure curve, then over here and over here, you have supercritical fluid. So, I don't know what the point is, okay? But it's moving around on your phase diagram. Carbon dioxide, yeah. So for carbon dioxide, I mentioned that it can be used as a supercritical fluid for extraction purposes. Notice that the critical temperature is pretty tame, 31. The critical pressure, though, is still pretty high, okay, 73 almost times atmospheric pressure. But you can just take kind of normal temperature carbon dioxide, pressurize it, and get your supercritical fluid. All right, so here's some substances and their critical temperature and pressure. Don't need to memorize these. You might refer to these in your homework, though. Don't have anything to add about that. One last topic to cover is this one. Water, since we're going to get hopefully we won't get a snow event, but somebody might get a snow event. Actually, depending upon the conditions that water crystallizes in, we can actually have kind of an assortment of different solids. with regard to ice. But if we focus just on the normal ice, ice Roman numeral 1, this is kind of what water's pressure, temperature, phase diagram looks like. And I think I mentioned maybe that water is actually a little bit unique. Can you see where the slope separating the solid and the liquid has a negative slope? Usually they have a positive slope. So that actually has consequences for ice skaters. Here's what it looks like. Basically, if you start out, if you do an isotherm, so stay at this temperature, okay, where P is, stay at the temperature, but go ahead and apply pressure. Can you see where at that same temperature, the greater the pressure, it's actually going to go from a solid into the liquid sector? Okay, so I mentioned ice skaters. So here's the deal. Basically, the ice skater has two blades, I don't know, about that long, about that thick, that the entire weight of the skater is resting on. So what the skater does is take, for a small area, a lot of pressure, the weight of the skaters. And if, I guess, heavens forbid, if they lift up 1 foot, they have all of their weight on one skate. Okay, so what happens momentarily, basically, is with that pressure, it liquefies, the ice liquefies underneath this blade. So,
So crazy.
so as they're skating around, actually they are creating their own little bit of liquid. Now, not to say it doesn't refreeze quickly, you know, depending upon the rink or the pond, you know, but
So it's not gouging it, it's melting it?
it is, to a certain extent, when the pressure is applied, it's changing its phase. Now, when the skater moves on to another location, you know, all bets are off. It's just momentary. Isn't that cool?
That's what makes jumps scary.
Yeah, I agree. So there's that, and there's that, in this liquid state. I'm not really sure what this means, but, so what this is saying, I suppose, is that if you go, I'm really not sure, because I get the whole weights and everything. Oh, I get, okay. So P to R is basically, you're ramping up the temperature, okay, and it's going to go to a liquid and then end up as a gas, at 1 atmosphere pressure. Okay. All right, so let's take a look at the problems. And I already told you, please do better than I did with some of these. But here are the hints, and I'll push them out there before I go today. 12:50. All right. So the first one looks like this, where you get to draw a sketch. Okay, it's for hydrazine. They give you some information about hydrazine. So there's the first part of my Y. Okay. It says that the density of the liquid is less than that of the solid. So that means actually you do end up having a positive slope. I've gone ahead and drawn my split between my solid and liquid in that fashion. Then I went ahead and put the triple point in. It gives coordinates of 2 degrees Celsius and 3.4 millimeters of mercury.
Do you want us to change that to ATMs?
See, that's a good point. I'll leave that up to you. It seems like you might want to, but I noticed that they go back and forth.
Yeah.
The normal boiling point temperature. So I left it millimeters of mercury, and then I did 760 is my normal atmospheric pressure in millimeters of mercury, and then I came down and drew the normal boiling point. So of course the boiling point is where it intersects your equilibrium vapor pressure curve right there, and I drew that in. That looked okay. I guess it's not as ugly as I thought. Critical point, it gives you the ordered pairs for that. No, it doesn't. It says, I guess when I did the critical point, it just says, are there any features of the diagram remaining uncertain? And I just put it right there where your equilibrium vapor pressure.
380 and 145.
What's that? Oh, yeah, it is. Yeah, thank you. Yep. That would be 380. And this would be, see, this is actually, and you're going to see, You can convert that to millimeters of mercury if you wanted to, or convert the other ones to atmospheres, it'd be cleaner. But on my diagram coming up, I just left them as mixed. And I didn't label, I just labeled the waxes as pressure. Because I'm like, yeah. This one's not too bad. Phase diagram for phosphorus. What are those sectors? Like, oh, okay, I think I can know what those are. That's A, that's pretty good. B is, it talks about how a solid, in its solid state, you can't, under normal atmospheric conditions, melt it. So, all right, 43 atmospheres. Oh my gosh, that's terrible. So you know actually 1 atmosphere's got to be down here somewhere. Well, to me it'd be down here. But 1 atmosphere is down here, and let's go ahead and say, you know, you go ahead and jack up the temperature. Well, if you jack up the temperature, it's going to go straight from what? Yeah, that's why it doesn't melt. Trace the phase changes. So if you go from A to B, you're going to start out as a thing and go into a thing and then end up as a thing. Okay, I don't mean to do your homework for you, but okay. This is where kind of like what, if you look down here, look, it like gives it 4.858 millimeters of mercury, and then it like talks about 218.2 atmospheres, like in the same paragraph. You're like, are you serious? And then here it talks about 2,045 atmospheres. That looks like a year, not a pressure.
Are you
But-
like supposed to talk about like maybe melting point and the critical point in different labels maybe?
What's that?
Are you supposed to talk about the points in like different labels or?
To me, I'm being, you know, it's up to you. You can't, to me, as long as you label each point with its units, that'd be fine.
I didn't know if it was like expected you, or like, in like the scientific field, talk about melting point in terms of millimeters per mercury and
Well, what I did was to recognize that 1 atmosphere is 760 millimeters of mercury. I used that as a reference point. So kind of as I went, I labeled things.
This is Common Core.
So, what?
This is
Yeah,
Common
well,
Core, isn't it?
it's Petrucci. It's a wonderful textbook. And, you know, but I agree. I'm not real thrilled with these mixed units.
Question A talks about TORs, and then B
Mm-hmm.
from 90 millimeters of mercury to 100 atmosphere. What?
Well, there's where you get to kind of pick. Do you guys remember what a torr is?
Yeah,
Okay.
it's the same as an atmosphere.
It's the same as a millimeter of mercury. So, I mean, it's not that it can't be done. And honestly, they might be throwing you into engineering mode where you're just, you got to figure it out. And it can be done, but you've got to think through it. So I think you're on the right track. So that's the one, use ICE 1 for A, and for B for your water. And for B, I pulled this one in for iodine. And it said, again, I don't like it, but it's kind of the way it is. Because it goes, see, look at the same problem, 90 millimeters mercury to 100 atmospheres. Like, really? But they're counting on you understanding that you know that 90 millimeters of mercury, it takes 760 millimeters of mercury to get here. So you figure 90 millimeters of mercury, and I think I maybe put it down here.
Crazy increase.
Yep. And it gave the temperature, and it's basically going to go from that low of a pressure to a, crazy increase, 100 atmospheres. But what's it going to do? And this was my best guess. So you guys work and kind of see what you think using that phase diagram. In other words, you turn something in, and if it's reasonable, I'll give it a nod. I'm definitely not going to go through these things with a fine-tooth comb. There are other chemistry problems where I can just definitely look at them and see if you were on track or not. This is not one of them. So this one is, you have 5 substances, and they are in the various solid, liquid states, solid, liquid, gaseous states. And for each one of those, kind of strewn a little bit throughout this chapter, I think, you have information like this. Or you have a physical phase diagram, or you have information like that to kind of make a judgment under normal Earth temperatures and Earth pressures, which again, Earth pressures is 1 atmosphere, 760 millimeters mercury or 760 torrs. Normal Earth temperature is 25 degrees Celsius, 298 Kelvin. So you're supposed to say any of these is likely to occur. Okay, again, given that physical phase that's in parentheses. So it's kind of it's not something you can sink your teeth into, but definitely can track it down. And you have to say why.
I'm sorry, so we're supposed to say whether or not CO2 solid would naturally occur?
Correct.
Okay.
And
got
it won't, we know carbon dioxide's a
yeah.
gas, so, but you need to justify why that is. And probably it has its own little, cute little diagram. You probably go on that diagram, find the normal pressure, normal temperature, and see what physical phase it's gonna be. Some of those other ones will be a little bit harder. So you
So we
can,
have to draw a diagram?
each one's gonna
Or-
be a little different, but I
Okay.
just said for carbon dioxide, there's a good chance that you're gonna see that, you know, normal atmospheric pressure, normal atmospheric temperature, it's gonna be a gas. That's the way you skin that cat. Now, these other ones may not have pressure, temperature, phase diagram. And you're gonna have to think through it with things perhaps like these critical temperatures, this table. It's a mixed bag. Yep. Okay. And we do have a study session Wednesday, so if you come, I'll let you guys get around and see what you come up with. Okay? Yay. You're welcome. Yeah, that was a terrible marker.
I didn't even know what you guys were talking about at first, and then I started to smell it, and I was like, oh.
Seagulls.
Sounds good. Yeah, that weather does sound wacky. Some of us gets rain and some of us get snow and
Increase the pressure. It's not.